All right. Hello, everyone. Welcome. Sorry, we are a little bit delayed. We encountered some unexpected technical difficulties, but now we are here. And welcome to the first in-person event of the semester of the Princeton AI Club. My name is Peng Ning. I'm the social care of the club, and I'll be introducing our speaker today, who really doesn't need any introduction. So he is the founding director of the NYU Center of Data Science and the Facebook AI Research at Meta. He's a member of the National Academy of Sciences and the National Academy of Engineering, and is co-recipient of the 2018 Turing Award for his seminal work on deep neural networks. So I present to you Professor Yann LeCun.
Sometimes it's complicated to connect to the Wi-Fi. You can't give a talk. And this position paper is basically my personal idea, which a lot of people may disagree with, of where I think AI research should go in the next 10 years or so, what the challenges are, and perhaps with some element of solution. But it's not really sort of a technical paper in the usual sense, in the sense that there's no experiments, there's no results, there's no proof of theorems. It's more like where I think things should go. And I wrote it in a way that would be readable, understandable, not just by computer scientists or machine learning researchers, but by sort of a wider audience, perhaps neuroscientists, cognitive scientists, etc. Okay, so the first thing is machine learning sucks, at least compared to humans and animals. The type of learning that we observe in humans and animals is clearly completely outperforms anything we can do with our or feeble machine learning techniques. And because most machine learning is based on, and most of the theory and everything is for supervised learning and reinforcement learning. And in my opinion, both supervised learning and reinforcement learning play a very minor role in the type of learning that we see in animals and humans. And we see this now. We arrive at the limit of supervised and reinforcement learning. Reinforcement learning requires too many trials. It works for games because you can play millions of games. It doesn't work in the real world. Or at least not well, and you have to kind of learn in simulation before you transfer. And supervised learning requires a lot of label samples, and that is limiting in a lot of situations. So that makes systems that are somewhat specialized and brittle, and they still make stupid mistakes. Now, and there is this big question that people have been asking since the early days of AI in the 60s, which is how do we get machines to have common sense? The type of common sense we observe even in your house cat. So animals and humans can learn new tasks very quickly. They understand how the world works to some extent, and they do have common sense. How do we get machines to do this? So those limitations might be due to the way we built our machine learning systems and also the paradigm of learning that we use. But one limitation is that the current crop of ML system does not really kind of reason. The output generally is computed with a finite number of steps from the input, right? You go through, I don't know how many layers, but there's no sort of internal reasoning that we could identify as reasoning other than kind of a fixed number of computational steps. And it's a problem when you want a system to be able to plan. So planning generally involves, optimizing, finding a sequence of actions that will arrive at a particular goal, perhaps minimizing some objective function. And this is not done by a fixed number of operations through a neural net. It's done by some optimization method. In fact, even in probabilistic models, like Bayesian nets and things like that, inference is done by basically optimizing likelihood or something of that type, right? I'm not talking about learning here. I'm talking about like deciding what to do next, deciding what output is best. As I said, humans and animals, some animals at least, understand how the world works, can predict the consequences of their actions through internal models of the world, can perform chains of reasoning with an unlimited number of steps, at least not a priori. So you might think animals are not capable of that, but they are. Your cat or your dog can actually plan fairly complex actions and sort of imagine the consequences of them before actually taking the actions. And they can do this hierarchical planning, which means decomposing a complex task into subtasks, all the way down to millisecond by millisecond muscle control. So how is it that humans and animals learn so quickly? Obviously, this is based, how is it that most teenagers can learn to drive a car in about 20 hours of practice, and we still don't have fully autonomous self-driving cars, despite our best efforts. And of course, the obvious answer to this is that we rely on our background knowledge about the world, right? So if a reinforcement learning system, were to learn to drive a car, it would have to run off a cliff a few thousand times before it realizes it's not a good thing, and then run off the same cliff a few thousand times before it figures out how not to run off cliffs, and then run off, a few thousand cliffs before it realizes that you don't want to run off any cliff. So that's one of the reasons why, reinforcement learning for autonomous driving has a limited role, essentially. So the difference is that, we know in advance that if we drive near a cliff and we turn the wheel to the right, the car will veer off and run off the cliff, and nothing good is going to come out of it, because we have this internal model of the world that allows us to make those kind of predictions. And how do we learn this model of the world? So this is a chart that was put together by my colleague Emmanuel Dufour, that tries to plot at what age babies can learn basic concepts about the world. It's very, things very, very basic, like, the world is three-dimensional, everything has a depth. When an object is hidden behind another one, it still exists, right? The notion of object permanence. If I take an object and I put it on the table, is it going to stay or is it going to fall? And things like the notion of gravity and inertia and things like this. So babies learn about things like gravity around the age of 9 months. If you show the scenario here on the left, where the car is on the platform and is being pushed off the platform and appears to float in the air, 6-month baby will, barely pay attention to it. The 10-month-old baby will go like this, will really sort of focus on it because it breaks her world model. The world model is that by that time, objects are not supported as supposed to fall, and there is an object that seems to float in the air. So how do we get machines to learn how the world works? By observation, which is really what babies do. Also by interaction, of course, but at first it's basically just observation. And in the first few months of life, we accumulate an enormous amount of background knowledge about the world. And perhaps this is what the basis, what constitutes the basis for common sense. So that leads me to essentially 3 challenges for AI and machine learning to kind of get them to the same level as humans and animals. The first one is learning representations of the world and learning predictive models of the world that will allow machines to, predict the consequences of their actions and then plan, reason, things like that, but also kind of understand how the world works. And I'm going to argue for the use of self-supervised learning for this. The second one is learning to reason. So we operate in 2 different modes, according to Daniel Kahneman, who's actually here at Princeton, Nobel Prize laureate in economics, and he argues for the fact that we can take kind of instinctive decisions very quickly, when we are used to kind of a task, we don't need to use a world model or anything. We just react very quickly. So after maybe 50 or 100 hours of practice of driving, you can drive without thinking about it, essentially. But in the first few hours of driving, you're completely focused on the task, and you use your world model to predict all kinds of catastrophe scenarios. And that's what he calls system 2. Okay, so system 1 is sort of reactive action, and system 2 is more planning and reasoning. And then the last challenge is kind of using those progress in those first 2 items to allow machine to learn complex, running to plan complex action sequences. So in the end, I think the whole idea of self-supervised learning, which I haven't explained yet, but many of you have heard of, I'm sure, I think plays a major role in this. And supervised learning and reinforcement learning actually play a very minor role. So I've been showing this slide for about 7 years now. It's become a meme in some circles. And so if learning in general or intelligence is a cake, the bulk of the cake is self-supervised learning. Most of the things that we learn in sort of self-supervised mode. And then a little bit of it on top, the icing, we learn through supervised learning. We're being taught, if you want. And then there's a tiny bit that we learn through reinforcement learning. It can only be a tiny bit because reinforcement learning is so inefficient. It's sample inefficient. And it's directly related to the amount of information that you ask the machine to predict for each sample, if you want. So in reinforcement learning, you ask the machine to predict a single scalar, which basically is a reward that you're going to give it. Okay. So the amount of information, feedback information you feed the system is extremely weak. And so that's why you require many trials to learn anything. Supervised learning, it's categories or whatever that are produced by humans, so it's necessarily limited in terms of amount of information. You get just a few bits per sample. And then in self-supervised learning, the idea of self-supervised learning is you predict the input, part of the input from other parts of the input. And so the amount of supervisory information you get is large. And so you constrain the system a lot. But before I talk about self-supervised learning, let me describe perhaps an architecture for kind of an autonomous intelligence system that, and then describe the various modules and how they, how they could work together. Okay, so this is what people used to call a cognitive architecture. I'm not going to make that claim. So the centerpiece of it is a world model. So the world model basically, given a current estimate of the state of the world and given a sequence of actions that you're imagining in your head, that the agent is imagining, what would be the result of taking this sequence of actions? So result in terms of new state of the world, but also results in terms of is it good or bad? And whether it's good or bad is measured by a cost function. Okay, so you have a module here, which basically tells the system this state of the world you're predicting is good or is bad. It's satisfying what you want to do or not. So the system that figures out what sequence of action, given the prediction given by the world model and given the cost, what sequence of actions will minimize this cost for according to the prediction, that's the actor. Okay, that's all the actor. Think of this of like what your reasoning system and premotor cortex does. All of this interacts with the short-term memory, which I'm not going to talk about that. And of course, there is a perception system that estimates the current state of the world. At the top here is a mysterious module called the configurator. And what this agent is has to be able to do is focus on different tasks at different times, because it's got only one world model module. And that world model module needs to be configured for the situation at hand. And that's done by the configurator. I'll keep this on hold for a bit until the end. Okay, so mode 1 is kind of like Danny Kahneman's system 1. Is sort of reactive action. So you observe the world, extract a representation of the state of the world using your perception system, and then run this through a So the policy module in the actor, and it produces an action. So it's completely reactive. There's no reasoning, etc. You might want to measure the cost of the predicted cost of the state, but that's okay. And then this is mode 2, and mode 2 is very similar to, for those of you who know a bit about optimal control, this is very similar to what people do in optimal control. So you start with the first estimate of the state of the world, and then you imagine the first action. From this first action, you can predict what the next state of the world is going to be. Then another action, predict what the next state of the world, etc. Right? So you can imagine a sequence of actions and the resulting sequence of state of the world, representations of the state of the world. At every time step, possibly you can run the state of the world through the cost function and measure the cost of this. And what the mode 2 system is going to try to do is figure out a sequence of action that minimizes the costs over the episode, the trajectory. Okay, it's very classical optimal control. This is how a lot of people do planning, for like planning rocket trajectories or robot arm trajectories and things like this. Now, the same way humans can, require to use their system 2 initially when they run a new task, and then as they get used to it, like driving, they can just do it without thinking. You can imagine a scenario here, and various people in the machine learning literature have done things of this type. You can imagine planning a sequence of action using your system 2 and your model of the world, and then using the resulting obtained optimal actions as targets to train a policy network, which would be reactive. Okay, so as you practice solving a situation more and more, and you figure out that what's the right set of actions, you can use that to train a reactive system that will just map the state of the world to an action for that situation. Okay, so in the cost module, there's sort of 2 submodules. One is called intrinsic cost, and it's immutable. It's just hardwired. It sort of determines the nature of the agent, if you want. And that's where you want to put safety constraints, for example, or sort of basic definitions of what tasks the agent is supposed to accomplish. But safety measures, or you can have cost functions that makes it pay for flaying a robot arm with a knife in its effector when you have people around, things like that, right? But also very basic things like avoiding pain, in other words, destroying itself, things like that, or finding a power socket when the battery is low. Sort of very basic things that you would imagine like most animals have hardwired. Okay, but they are in the form of cost functions. They aren't in the form of hardwired behaviors. They are in the form of cost functions that the behavior has to satisfy. Okay, then there is another part of the cost, which is a trainable cost, sometimes called critic in the reinforcement learning literature. And this is meant to basically predict ahead what the value of the intrinsic cost is going to be. So if I approach you and I pinch your arm, okay, you're going to be very surprised. And you're probably going to kind of update your cost function, giving a high cost to my proximity to you. And the next time I approach, you're probably going to recoil, right? So that's probably your critic kind of learning a cost function that says, you don't want me anywhere near you. And you can train the critic by basically having a short-term associative memory, or perhaps long-term actually, that I apologize for the mess here, but that whenever you have a state of the world and you measure the intrinsic cost, you can store it someplace and then wait for it, and then you can measure the intrinsic cost again, and then use the intrinsic cost in the future to train the predictor, the critic. I mean, you can imagine all kinds of sophisticated ways to do this. Reinforcement learning has, entire books about how you precisely do this in the sort of actor-critic type architectures. Okay, but really the main issue in all of this is how we build and train the world model. And the main issue there is that the world is stochastic, or at least if it's not stochastic, it's not entirely predictable because it's not entirely observable, even if it's deterministic. So this is going to lead me to argue against using generative models. And generative model are kind of a big pillar of machine, one of the big pillars of machine learning, but I'm going to argue against it. Okay, so what's a generative model? A generative model is something that predicts y, okay, the variable you want to predict from possibly an observation or possibly from nothing. But it makes a single prediction. Yeah, at least in the case of deterministic generative model. So you have a neural net, it's a parameterized function. You give it an x, it produces a y tilde, and it produces only one y tilde. Okay. Now, if the world is non-deterministic, like I do the experiment where I put a pen on the table and I let it go, every time I do the experiment, the pen will fall in a different direction. And so if I force the system to make a single prediction, it's going to have to predict perhaps the average of all the possible plausible futures. And that's not a good prediction. In fact, when you train a neural net to predict the future, well, this is a neural net that's been trained to predict the position of cars on the highway from a top-down view. And what you get is sort of blurry prediction because the system has no idea whether the cars are going to accelerate, right turn, etc. If you train on natural video, you get the kind of results you see here. The first 4 frames are observed, the last 2 are predicted, and you get very blurry predictions. Okay. So of course, immediate instinct for a lot of people in machine learning is to say, yeah, of course, right? You don't want to build a system that makes a single prediction. You want to perhaps have it predict a probability distribution. Yes, except that we have no idea how to parameterize proper probability distributions over the set of all possible video frames, for example. We can do it when we predict words in a text. We have no idea how to do it to predict something like a video frame, like a high-dimensional continuous object. And the problem is that we don't know how to normalize those distributions, essentially. Okay, so we hit a fundamental problem that physicists have encountered since World War II and statisticians also for quite a while, which is that we can parameterize very complex distributions over high-dimensional continuous spaces, but we need to normalize them. We need to make sure they integrate to one, and that we don't know how to do. But before I propose a potential way around this, let me talk about self-supervised learning and why self-supervised learning needs to deal with this question. So self-supervised learning really is the idea of capturing dependencies between inputs. You don't have inputs and outputs, you only have inputs, or you only have outputs, really, and you want to capture the mutual dependencies between everything. So, so think of it in terms of masking. So you have a piece of data, let's say a video, and at first, the system only sees a portion of that video, perhaps the beginning, not the end. Okay. So thinking of a video as a volume, you observe the purple stuff and you don't observe the blue stuff. But it's not just predicting the future. You can imagine some sort of random masking that every time you see a new video, different parts are masked, and you don't know in advance which one. And the game in self-supervised learning is predict the stuff that is masked from the stuff that is not masked. So if the stuff that is masked is always the same, you call it X. If the stuff that is masked is always different, there is no X, everything is a Y. And what you can do with self-supervised learning is, learning hierarchical representations of the world, learning predictive model, hopefully. And the question is, how do we handle uncertainty and multimodality? And for this, my solution is energy-based models. So energy-based models are kind of a framework that you can think of as sort of a weakened probabilistic framework, where we don't insist that distributions be normalized. Essentially, you can think of it this way. Okay, so how are we going to use this? Basically, we'll have, so let's say we're doing something like capturing dependencies in video. So we always observe the past and we want to, in the present, and we want to predict the future, or at least capture the dependency of the future to the present, to the past. So what we observe with X, what we don't observe with Y, that's what we need to predict. In fact, we might be observing Y at some sometimes, but X is always observing. And what the energy-based model is function f of xy that gives you low values when y is compatible with x. So, for example, in video, when y is a good continuation for the video clip x, and gives you higher values when y is not a good continuation. Okay. So think of it in these terms. Let's imagine that x and y are both scalar, and those are the data points, the black dots. You want your f of xy model to give low energy to those points and regions around it, and then higher energy outside, and that's represented by those level curves. Okay, that's an energy-based model. You can turn this into a probabilistic model if you want in some cases, but we're not going to do it. Okay, so how do we do inference in an energy-based model? So first of all, we don't always have to do it, because the point is rarely to actually predict y, and I'll come to this in a second. But if you really want to predict y from x, what you have to do is basically, for a given x, find a y that minimizes f of xy. Okay, that's how you do prediction. So here are two different energy surfaces that capture a dependency between x and y, which is here y is a function of x. And those actually have the same role; they capture the same dependency. Okay, but they're both perfectly fine at giving the lowest energy to for a given x, the lowest energy is given to the data samples and the regions around them, and then higher energy for everything else. So basically, energy-based model is some sort of implicit function, right? And the advantage of this is that you can represent multimodality easily. So for a given x, you can have multiple y's that have low energy, and you don't need to force the system to make a single y prediction and then force it to make blurry prediction. Here, you just capture the mutual dependencies between the variables. So the nice thing about this energy-based model view is, or energy-based view, is that there's a lot of classical algorithms you can reinterpret in those terms, like k-means and mixture Gaussian spot coding, all kinds of stuff. So actually, that's an example of an energy function in 2 dimensions, where the data points. So this is the k-means algorithm that was trained, and the energy function here represents the surface. So the dark is low level, and then the bright is high level. And those dark regions correspond to the case where you have prototypes obtained from k-means, and the data points are sampled from the spiral in this particular example. You have conditional and unconditional versions of energy-based model. The unconditional version is when there is no x. So you can transform easily or not easily in energy-based model into a probabilistic model by, for example, using the Boltzmann distribution. So here, y given x would be the exponential minus the energy of x and y multiplied by some coefficient, which is similar to the inverse temperature. And then you have to normalize to make sure that the integral of this over y is 1, right? So if you compute the integral of this over y, you get the same thing on top, and that becomes 1. It's pretty familiar formula. This is like continuous submax. In most cases, for most functions f and continuous y's, you just cannot compute this. It's intractable. Okay, so we're just not going to do that. Okay, within a energy-based model, you can have latent variables. So you can define the energy between x and y itself as being some minimum with respect to some other variable z, which we'll call a latent variable. So z here is just an input. It's not observed. It's never observed. And it's an input to an energy function that has 3 parameters. When you minimize this energy function with respect to z, what you get is a function f of xy that does not depend on z anymore. Okay, but the internal process of measuring the energy, if you want, f of xy involves a minimization with respect to latent variables. It's important for the rest. So how do we train an energy-based model? We can do things like maximum likelihood, whatever, because we're not in a probabilistic framework. But it's not that complicated to understand. Basically, we have to make sure that the energy surface is going to take the right shape. So we want low energy for a training sample. So we're going to show a training sample to the system. Our energy function is going to have some parameters. We're going to tweak the easy to do. We can do an descent, we can backprop. Or energy function can be some complex neural net, doesn't matter. We can make the energy of the training samples low by gradient descent on the parameters. But how do we make the energy of everything else higher? So there's two approaches. One approach is called contrastive method. So contrastive method consists in generating those green points at various places. And then those green points will be outside the manifold of data. And you push their energy up. Okay, so by pushing down on the data point and pushing up on places outside the data manifold, eventually the energy function is going to take the right shape. This is a general form of what's called contrastive methods. You might have encountered the idea of contrastive method in sort of restricted case, but this is sort of the general formulation if you want. But then there's another approach called regularized methods. And regularized methods work by essentially through a regularizer or some architectural constraint or something like that, it minimizes or restricts the volume of space that can take low energy. So if you push down on one part of the space, the rest will necessarily go up because the total volume of space that can have low energy is limited. Okay, and I'm going to argue for regularized method because I think contrastive methods have a major flaw. So let's take some standard architectures and see to what extent they can be subject to collapse and whether we have to use contrastive methods or regularized methods. So a standard prediction or regression architecture, a neural net. Okay, let's imagine this is the first few layers of the neural net, and that's a few more layers. And then you measure the distance between the output and the y. That cannot collapse. It cannot collapse because for a given x, this system can only give low energy to one single y, which is the y that it predicts. Every other y will necessarily have a higher energy, the energy being the distance between the predicted y and the output. Okay, so I use the symbolism here, which is basically inspired by factor graphs and graphical models, where a module that has a rounded output is a deterministic function. Think of neural net, some parameterized function. A bubble is a variable, and a square or a rectangle is a cost function. Okay, and the overall it's an additive term in the energy function, right? So that the overall energy of the system is the sum of the outputs of each of those squares. I don't represent the output, we only have inputs to the computed distance. So think of this as computing some sort of divergence between y and y tilde, and that's the energy function. This cannot collapse by construction because it can only give low energy to or zero energy to a single y. Every other y will have higher energy. Now let's think about a latent variable generative model. So this is the generative model. It's a generative model because it produces y directly, it predicts y, but we allow y to vary for a given x. We allow multiple y's to be produced by basically the use of a latent variable. It's not a probabilistic latent variable necessarily, but it's a latent variable that can vary over a set. And as this latent variable varies over the set, the prediction varies over another set whose dimension is lower than the set of z. Okay, so if I give you an x and a y, what you do is find a z that minimizes the prediction error. Okay, and that's your energy, right? That's what I explained with latent variable models. This can collapse. It can collapse because imagine that z has the same dimension as y, and that the predictor is not degenerate. then the predictor can just run the identity function. Now for every pair xy, I'm always going to have a z that produces y hat equals 1. Okay, so the set of y hats basically is the set of all y's. And what that means is that the entire set of y now is 0 energy. Okay, so if my latent variable is too powerful, has too much information in it, can span a large set, then my model can collapse by giving 0 energy to everything. And that's bad. To correct this, I would need to limit the information content of Z. Make it low dimensional, sparse, noisy, whatever. This is an autoencoder. So autoencoder is no X, it's unconditional. You take Y, run it to an encoder, get a representation, run that to the decoder, reconstruct. This can collapse. I don't know if you've ever tried an autoencoder, but if you don't regularize the autoencoder, it will learn the identity function and will perfectly reconstruct everything in your space, which means it gives a flat energy surface to everything. It's not good. What you want is, when you train an autoencoder, is that you want your autoencoder to reconstruct what you train it on, and you want it to not reconstruct anything you don't train it on. You want it to reconstruct it badly. Okay. So to do this, people invented, contrastive methods like, using autoencoders, which is used in the BERT models and things like that. Or a good example of this that is making a lot of noise today is diffusion models. There's a special case of that. Or you can regularize your autoencoder by making sure that the representation here as a low information content is low dimensional, for example, or noisy. So if you make it noisy, you get something called a variational autoencoder. Okay, and then you have this other type of architecture called the joint embedding architecture. I'm going to spend some time on this. So here you run both X and Y two encoders. And then at the output, you say, if X and Y are compatible with each other, I want the two representations to be equal, or at least easily predictable from each other. Okay, you may have heard of Siamese networks, or things like Moko, Cynthia, Perl, whatever. I mean, there's a whole bunch of self-supervised methods for vision in particular that use those joint embedding architectures. Okay, but really we only have two categories of methods to train those energy-based models, or to train probabilistic models for that matter. Contrastive methods and regularized methods. Contrastive method again, generate state points outside the manipulated data, push their energy up while you push down the energy of the training samples. And then regularized methods have some sort of way of minimizing the volume of stuff that can take low energy, a sort of level set of low energy, if you want. So example of contrastive method, so this is the first paper on this go back to the early 90s, so it's not recent, is take 2 points, Y and Y hat. So Y hat is going to be a contrastive point, one of those green points. Y is going to be a data point for the next. And then your last function is going to be something like this at the top. This is called margin triplet loss or something like this. So you have the energy of the data points minus the energy of the contrastive points. And then you add a margin that may depend on the distance between Y and Y hat, for example, and then plug this to a value, take the positive part, okay? So it's like a hinge. So what this cost function wants to do is make the energy of the training sample low, make the energy of the contrastive sample higher by at least m. Okay, and if it's higher by at least m, then the cost is 0. Okay, so that's an example. And then the regularized method, I'll talk about later. Okay, so this is a eye chart, which I don't expect you to read, that it tries to list all the classical methods that you may have heard of as to whether they are contrastive or regularized. And things like all probabilistic methods based on Monte Carlo sampling or Markov-Chain Monte Carlo or Hamiltonian Monte Carlo, they are all different ways of sampling negative samples, the generative green bands. Okay. Contrastive divergence, it has even the name contrastive in its name. Metric learning and Siamese nets are the classical type, circa 1990s. ratio matching, most contrastive estimation, blah, blah, blah. GANs are an example of contrastive methods. Matched autoencoders like BERT or denoising autoencoders, those are contrastive methods as well. I'll show you why. And then regularized methods, there are things like Gaussian prediction models for RCA, known as inflow, PCA techniques, sparse codings, sparse autoencoders, and then a whole bunch of new methods have been applied to joint embedding architectures for vision and with very good success. You know, variational autoencoders, things like that. And then two methods that came out of my group at FAIR, which means it's big brain. Okay, so let me go quickly on contrastive methods because they're popular, but I'm going to argue they're not good. So again, generate those green points and push them up, and then while you push down on the blue point. But you can do this with a lot of different cost functions. Okay, everybody seems to be using InfoNCE, but you don't have to. People over the years, starting perhaps in the work on discriminative training for speech recognition, have been kind of dreaming up those cost functions for decades. So I'm not going to go through the entire list, but I just want to make the point that there is a whole bunch of those, and you don't have to always use the same. But this is the one that is popular at the moment, and it's called InfoNCE. So basically, you take a bunch of you take a positive y, and then somehow you come up with a bunch of negative y's. And what you do is you plug those energies into some sort of softmax function, log softmax function, so that by minimizing this negative log softmax of e to the minus the energy of the good guy divided by the sum of the energies of the bad guys, this is going to push the energy of the good guy, push down on it, and then those energies will get pushed up. And so this is what people use in things like SimClear and all those Siamese methods, which I'll talk about in a second. So as I said, you can turn a probabilistic model, you can turn an energy-based model into a probabilistic model, but it's actually not good to do that because the ultimate solution of your minimization process, if you do maximum likelihood, wants to arrive at an energy surface which gives the lowest possible energy to your data point, and then the highest possible energy, possibly infinity, to anything just epsilon away from the manifold of data. And so what you get as an energy surface, if you use maximum likelihood in a probabilistic context, is that you get deep canyon for your energy function. It's not good for inference. It's not helpful. It might capture the distribution of your data, but it's not what you want. You don't want to capture the distribution. You want to capture the dependency. It's a much weaker concept in some ways, but more useful. Okay, so so far I've argued against two things. I've argued against the probabilistic framework. Okay, and Aji is going, oh my god, but she's used to it. But she's heard me say this before, so. Yeah, so GANs are an example, but I'm not going to talk about this for like a time, but here is a good example, denoising autoencoders, right? So denoising autoencoder, the idea is you take a training sample, let's say from one of the blue points here in the spiral, and then you corrupt it in some way, right? By, for example, adding noise to it. So you get one of those ground points. And then for 1 pair of points, you push down on the blue point and you push up on the ground points. So the way you do this with a denoising autoencoder is the particular way. You run the ground points through the neural net, which you train to reconstruct the blue point. And so what that means is that next time around, when you show the ground point to the system, it's going to reconstruct the blue point, and therefore the reconstruction error will be large, right? So you train the system to produce a reconstruction error, an energy, which is basically the distance between the blue point and the ground point. Okay. So BERT systems work this way, right? It works with text. You take a piece of text, you mask portions of that text, replace the words by blanks, and then train this autoencoder essentially to recover the missing words, predict the missing words. And that's a denosing autoencoder. So it's an example of contrastive method. It works in the case of text because text is discrete, so there aren't many different ways to be different from a good text. And you can easily handle uncertainty in the prediction because text is discrete. You only have a finite number of words in the dictionary. You can do a giant softmax over all the words in the dictionary, and that's how you represent uncertainty. We can represent distributions over a discrete set easily. We cannot do this over the set of all images, let alone videos. So this type of pre-training of text NLP system has been ridiculously successful over the last 4 or 5 years, as many of you probably know, and has brought about like enormous progress in things like translation or text generation and things like this. This is an open source model that was recently produced by my colleague at FAIR, 175 billion parameter language model. So this one just predicts the next word, but it's also been trained to just fill in the blanks, and then used the internal representation was used as input to various downstream tasks in NLP, like say hate speech detection. Big boost in hate speech detection. You might think that it's very useful for Facebook, and it is. And it's made a huge amount of progress in the last few years. So Facebook rate of hate speech detection, preemptive hate speech detection using NLP system 4 years ago was about 30%. Now it's 96.1. And it's pre-trained BERT. Another project recently open sourced also by my colleagues at FAIR, No Language Left Behind. So this is a translation system that can translate from like 202 languages from any language to any language. But it only has training samples for 2,400 of those pairs, of those 40,000 directions. There's 40,000 directions, but you only have training samples for a small subset. And through pre-training, you can actually get a system to kind of translate fairly reliably. This is the list of the 202 languages that are handled by this system. There's a whole bunch of those languages. I have no idea where they come from. And many of them are what's called low resource languages. So there is like very little parallel text of those languages to other bigger languages. So the obvious idea, of course, is to use the same system to pre-train a vision system. Okay, take an image, corrupt it by blocking some parts of it, and run through an autoencoder to recover the clean image. And that basically doesn't work very well, except in one particular exception, where you break the image into batches. You run your autoencoder is happens to be a transformer architecture, and what you mask are different parts, input tokens of the transformer. So that's called MAE, masked autoencoder, and it works okay. It's not great, but it works okay. It's difficult to scale though. Okay, so now that I've told you to drop probabilistic modeling, I'm going to tell you to drop generative models. Okay, so here are two different architectures. One is generative, so it produces a prediction for y. If you want this to be non-deterministic, you need to have a latent particle, okay, which I'm not representing. And this is the joint embedding architecture, where you run both x and y autoencoders. And what you measure is the divergence between the predicted representation of y and the actual representation of y. And there's a crucial difference between those two things. This guy, when you train this guy, you need the system to predict every details of y. Okay? Regardless of how complicated it is. Whereas here, it's possible that this system might be trained so that the encoder drops a lot of information about y on the floor, perhaps information that's irrelevant or too complicated to capture. And so now what the system needs to predict through its predictor is basically an abstract representation of y that may not contain all the information. Okay, so this cannot collapse unless you add a latent variable, in which case it can collapse, and you have to prevent that from happening. But this can collapse. So if you're going to use this, you're going to have to figure out how to prevent this from collapsing, either using contrastive methods or regularized methods. Now, so why am I going to argue for this? So let's imagine that what you want to build is a system that can predict what's happening on the roads. Okay, it's a self-driving car, and the self-driving car has to be able to predict what's going to happen on the road, in the next 2 seconds or so, so that you can, drive defensively. Right, there's a big truck in front of you, and it's going to swerving. Your model of the world is stay away. Right. Okay, that's what I did when I came here. And things like this. Is the car in front of me going to brake or accelerate? Is it going to is it going to a fork in the road? Is it going to turn left or right? Can I do something ahead of that? Stuff like that. Now, when the car drives down the street, there might be relevant things like cars and pedestrians and various other things. But then bordering the road, there might be trees, and there is wind today, so the leaves of the trees are moving. And if you have a generative model, your system is going to have to predict every single leaves of the tree, which of course is not only a useless task, but also a very, very difficult, complicated task. Okay, if I'm pointing the camera here, just at the floor, and I'm kind of moving the camera, and I want to predict what's going to happen next, I have to predict all the details of the texture of the carpet, which of course is completely irrelevant to any task you could imagine, unless you clean the carpet. So it would be very useful for a predictive model to be able to decide a priori to abandon information that is just clearly not predictable, or would require too much resources to predict. Okay, let me skip this. Okay, so we have now, so I've been arguing for this joint embedding architecture, essentially, and there's really 3 forms of it. One is called the joint embedding architecture, sometimes known as Siamese networks, if you enforce the 2 networks to be identical and share the same weights. Another one called deterministic JEPA. So JEPA stands for joint embedding predictive architecture. So the difference is that you're a predictor. So instead of forcing the 2 representations of X and Y to be equal, you only force them to be predictable from each other. Okay, to make Y predictable from X. So the representation of Y predictable from the representation of X. So that's deterministic. And then the full JEPA, the joint embedding predictive architecture, which may or may not be deterministic, has a latent variable here that allows to make multiple predictions for SY given a single observation. So you have a car in front of you. You have no idea if the car is going to turn left or turn right or go straight. That would be a latent variable that it can take 3 values. Okay. Once you observe, then the latent variable is determined. But regardless of what representation you have of the world, you might need this latent variable. You will need this latent variable. Okay. So contrastive methods, work really well. So as I said, the first papers on this go back to the early 90s. There were a couple of papers in the mid 2000s from my lab at NYU, and then some more recent work, going back 6-7 years, for training image recognition system. And there's sort of various flavors, which I'm not going to go into the details of. But the basic idea is of those contrastive methods is as follows: you take a pair of images that has the same semantic context. They're obtained by distortion of a single training sample. And you train the system to produce identical representations for the 2 things. And then you take negative pairs and you push the 2 representations away from each other. And you can have a choice of which loss function you use. As I said, people use InfoNCE most of the time. And then you chop off the top layers or layer and use a representation as input to a subsequent downstream classification task, like say ImageNet classification. And this works reasonably well. And you can get sort of better performance on ImageNet object classification than you would if you train purely supervised from random initial condition. But what you have to do is pre-train on a very, very large number of samples. So if you pre-train on ImageNet, you don't get an improvement over purely supervised ImageNet. If you pre-train on like 1 billion photos from Instagram, self-supervised, and then you fine-tune on ImageNet, then you get a boost. This works really well also for speech recognition. You can now train a speech recognition system, or speech recognition systems that are multilingual, so they handle a lot of different languages, and they can be trained with something like 10 minutes of annotated speech in any particular language, thanks to various self-supervised pre-training methods. Okay, now we'll talk about regularized method, and that's really the cool stuff. So we're going to focus on this architecture, the JEPA, whether it has a predictor or not, whether it has a latent variable or not. And the basic idea is going to be that to prevent collapse of those things, we're going to use some measure of information content of the representations of both X and Y. And we're going to try to maximize the information content. Okay, the problem is that we don't know how to measure information content, so we're going to have to use tricks, but basically that's the idea. Try to make the representations coming out of the encoders as informative as possible about X or Y. Okay, so that's one term. The second term, of course, is the prediction error. And then if you have a latent variable, the third term would be a measure of the information content of V, but then you need to minimize it if you want to prevent collapse. There's been a bunch of methods that have been proposed over the last 2 years or so that kind of do things like this. BYOL is a bit of a different animal, but Barlow twins, VicReg, and WMFT. And let me talk about VicReg because that's my favorite method at the moment, and not just because it came out of my lab. This was an IKEA paper, 2022, but the paper has been on archive for longer than that. And basically, the way this works is the criterion that is being minimized here is a criterion that tries to make the covariance matrix of the SX over a batch as close to the identity as possible. Okay, so you want basically every variable coming out of your network, you want it to be essentially variance 1 or standard deviation 1. And then you want all those variables to be decorrelated from each other. This is a bad approximation of information content because you should have very complex nonlinear dependencies between variables, not just correlations. But it seems to work. Okay, so those criteria are differentiable. You can just backpop to it. So there is this module here. It's called an expander, and the role of the expander is basically think of it as a neural net with a few layers. They may have residual connections, and its role is to increase the dimension of that representation so that when you decorrelate the components of this Vx that comes out of it, you actually make the components of Sx more independent of each other. It's a bit of a wishy-washy argument, which I'm not going to go into, but we're still figuring this out. And this works pretty well. So these are experiments where you pre-train such a system on ImageNet with a particular type of data augmentation to generate the pairs that you want to be identical to each other. And those are various self-supervised methods that have been applied to object recognition. And this is the performance you get on ImageNet by fine-tuning by training a linear classifier on top of the representation, trained self-supervised. So it's not record-breaking, but it's a good way of assessing the quality of the representations that are. And this is by training only on a small number of samples. But, so they're all in the same ballpark. All the top methods around 73, 74. Swab is a bit different. This is from Paris, and this is a little dog because they use a technique called multi-crop, which you could also use for other methods. And you can use those features that are learned as input to other tasks that are not object recognition, but things like detection, classification, etc. There's various advantages that I'm going to skip. Coming to the end. So let's go back to the architecture I was talking about earlier. Really what we want to use JPA for is to train word models. Okay, I can't show you examples of that actually working because we don't have them. As I said, this is more the position paper, but I mean, VCREG is an actual paper. But this whole cognitive architecture is kind of more the future for what we're doing at the moment. One idea with JPA is that you can stack JPAs. So you could imagine having a relatively shallow network making short-term predictions in videos, for example, and then generating more abstract representations with a few more layers, but then using this to make longer-term predictions. So, for example, if I want to go from here to New York City, I drove stupidly, so I can predict approximately it's going to take an hour and 20 minutes or so. There's no traffic. I can't predict all the details, but I know that I'm going to have to take Route 1 and then, the Turnpike and whatever and Holland Tunnel. Okay. So at a high level, I can make a description of the sequence of action I need to, or conditions I need to fulfill. But I can't say precisely what will be my millisecond by millisecond muscle control of my wheels and pedals on the way there. That, whether a particular light on Route 1 is going to be red or green. So there's a lot of details that I'm not going to consider. But half a second before I encounter the lights, I can tell whether it's going to be red or green. So I can make short-term prediction with a lot of details. But for long-term prediction, I need to kind of abstract away a lot of details. But it's this kind of hierarchical abstraction that would allow an intelligent agent to do what's called hierarchical planning, which means you have an overall objective, which is symbolized by this cost module here at the top, going to New York City. And you can decompose this into subtasks, one of which is go to Route 1, and then once you're at Route 1, take the Turnpike. And then to go to Route 1, I need to get out of this building, go to my car, drive the car to east towards Route 1, and then turn left, things like that. So, and then all the way down to millisecond and millisecond muscle control. So you could do hierarchical planning if you had a word model that also was hierarchical, and this is what JPA might offer us. Of course, the world being non-deterministic, there will be all kinds of latent variables in there that correspond to all kinds of possible scenarios that you might have to imagine ahead of time. Okay, so this is the last 3 slides. So steps towards autonomous AI, self-supervised learning is going to be a key component of it, to learn representations and to learn predictive models. Handling uncertainty in prediction using joint embedding architectures, not generative models, and using the energy-based framework, not the probabilistic framework. Learning world models from observation as much as possible, because any action you take can kill you and is expensive in the real world. Then doing this reasoning by kind of finding a sequence of actions or latent variables that minimize a particular cost. That's a form of reasoning. So now we would have a system that is both capable of learning, it's a big neural net, but is capable of reasoning as well. And this is sort of one of the big critiques that people from sort of more traditional AI, old-style AI, if you want, have said against sort of neural net deep learning approaches, which is that, where is the reasoning? Can those systems actually reason? I view reasoning in this case as basically a form of energy minimization with respect to latent variables, which is very similar to what people do in, probabilistic graphical models and factor graphs and stuff like that. And planning is a form of reasoning in that case. Now here's some speculation here. So I'm imagining here that the system only has one world model, but that world model is configurable for the situation at hand. And it looks very much like this is the case in humans. So humans, we can only attend to a single task at a time, right? Conscious task, if you want. Right? When we're focusing on this task, we can basically only do this one conscious task. We can do subconscious tasks simultaneously, but there's only one conscious task we're going to be able to do at any one time. And the hypothesis, which maybe is crazy, is that we only have one world model engine in our head. It's configurable for the situation at hand, but we have one engine. And because we only have one engine, we can only do one conscious task at a time. There's various theories in philosophy of mind and cognitive science that kind of jive with this, but and so the funny thing about this is that consciousness would be a consequence of a limitation of our brains. Basically, we only have one world model engine. We're conscious because we're stupid, not because we're smart. Here's more crazy conjectures and hypotheses. Prediction is the essence of intelligence. I think it's easy to convince yourself of that. Almost everything can be learned and is learned. Hierarchical Japa, perhaps using non-contrastive method. I think I'm kind of putting my money on this. I may be wrong. Almost everything is learned through self-supervised learning. Only very minor thing I learned with supervised and reinforcement learning. Intrinsic cost in the architecture is what drives behavior and determine what the agent will learn. And this is true also for humans and animals. And those systems, if we build them, will actually have emotions, because emotions essentially are anticipation of outcome. You can think of it this way. And if you have a system that has a critic and then plans actions on the basis of what the critic predicts, it will certainly have the equivalent of emotions. Reasoning is an extension of simulation, prediction, and planning, optimal control. And consciousness exists because we only have one world model engine. Okay, so those are crazy hypotheses, speculations. You don't have to believe me, but it's fun to think about it. Thank you. Yeah, I should say, don't try this at home, in the sense that this is the kind of stuff you can say in front of an audience when you are over 60 and Turing Award winner, but not so much for our graduate students. All right.
Does anybody have questions?
Thank you so much for that. I'm going to ignore all the really great machine learning stuff we talked about and just focus on consciousness because it's so interesting.
Okay.
So the hypothesis is we can only have one world model active at this time. And that's like what gives us like conscious, like single track attention. In the Java Commerce Science Cognitive Control Lab, where I'm in expectation, we have some models where you can multitask and like they're looking for when things can test and when they can't. I'm not going to get into that, but I'm just wondering, like, does it really matter what humans can do and why they can do it if like the future artificial intelligence is going to be artificial intelligence with like vastly different constraints than human neurons and human neurons?
Well, I mean, I think there are essential characteristics that are the same. So, I mean, you need the system to be able to reason and plan. You need them to understand how the world works, because they can't plan if they don't understand how the world works. There's a lot of people who are arguing for the fact that intelligent systems need to have some form of causal inference. So being able to say, like, if I take this action, will I obtain that result, which basically is what the model of the world is, some sort of causal model. That's if we want machines that reach something close to, I'm not saying necessarily human level intelligence, but just the level of intelligence of, or cats. Okay, they can do all that, and our machines can't, and that really limits what we can do with them. So I think those characteristics, and then there is the argument that okay, we've known how to do reasoning since the 1960s, but the problem I'm trying to solve here is, can we come up with a form of reasoning that is compatible with deep learning, basically with sort of differentiable functions and stuff like that, that can be implemented, with some big neural net, even though it has a particular architecture. So that sort of rules out more classical approaches to reasoning, like symbolic manipulation and stuff like that, right? Which, you probably heard about. Gary Marcus has been sort of counting at this thing that AI systems should incorporate some explicit symbol manipulation mechanisms. I don't think that's the case. Maybe I didn't answer your question.
We're talking about the human machine intelligence. Is that restricted in terms of scope of problem you can solve. But by that I mean, does that include, for example, discovering mechanisms behind design? Would that fall under the autonomy?
In one way, it would. Maybe not the autonomous part, but at least the part of understanding causal models and predictive models. Certainly, yeah. Yeah, I don't know. You want to, synthesize a new compound that might be, a catalyst for separating hydrogen from oxygen. I'm citing this example because actually people working in the sector, or a new material for more efficient batteries, something like this. You might want to have some sort of phenomenological model of if I mix those two chemicals together, will I get the chemical I want in the end? If I heat up, blah blah blah. So learning phenomenological models of physical processes, I think falls into this category of learning world models, which you can use afterwards for planning. But really, there's nothing new to this. That's optimal control with systems identification. What's new about it is that we use large neural nets instead of linear models with a few parameters.
Hi. So you are in your talk, you argued for the energy-based models in the Java architecture. I was wondering, do you is there anything you feel is what are the limitations of that approach? What do you think are the limitations, or what's preventing them from becoming more mainstream?
I think they already are mainstream to some extent. They're just not formulated this way. So you can think of, things like K-means is mainstream, PCA is mainstream, BERT is mainstream. So there's a lot of methods like this, and they are viewed as sort of isolated examples of a trick of trying to train a neural net or a particular model or whatever. But in fact, it can all be understood within the context of this energy-based framework very easily, in terms of they all have different ways of making the energy of stuff you train on low, and then the energy of stuff you don't want higher. And I've classified this into those two categories, right? Contrastive and regularized. And I can't think of anything else. All the methods that people formulate, including all the probabilistic methods, fall into one of those two categories. It can be understood in those terms. And you don't have to have 2 pages of relational approximation, blah blah blah. It's very easy to understand how they work. So now, what's the limitation? We don't know in what conditions. Here's why I should have argued, but I didn't, against contrastive methods. I forgot to admit. Is that if the space of representations that you manipulate, the SYs or whatever, is high dimensional, the number of points or contrastive points whose energy you're going to have to push up might become very large. It might actually grow if you have an infinitely flexible energy function. It's a very, very large neural net. Then the number of points whose energy you're going to have to push up grows exponentially with the dimension of the space. And so if you just think about it in those terms, contrastive methods are doomed, because they're going to be basically caught by the curse of dimensionality, at least for powerful models. Which is why I'm sort of more in favor of the regularized methods. But I'm not sure I'm completely right about this, because a bunch of students and postdocs are working on kind of trying to sort of figure this out, and they actually show some sort of duality between contrastive and non-contrastive, so we don't know what the answer is here. So there are sort of theoretical, the formalism being weaker than probabilistic methods. There could be situations where it doesn't work and you don't understand why. There is no generalization bounds and stuff like that, although there is no reason why they shouldn't. So, if you're interested in theory, the landscape is completely new. It's completely open. We just worked on it.
In your talk, you mentioned that maximum likelihood methods create deep canyons in the energy content. You said something to the effect of this approach capturing distribution but not dependency. I was wondering if you could clarify that.
Right. Okay. So imagine that so, okay, if you take millions of photos and you take 5x5 pixel patches from those photos, and you ask the question, so you can have, zillions of those patches, right? It's a 25-dimensional space, at least for grayscale images. And you ask, are all combinations of 25 pixels possible in photos? And the answer is no, very far from it. So the 25-dimensional space of 5x5 image patches is not filled by the set of all natural images. It's a submanifold in this. Now, if you have noisy images, that manifold has some thickness. But we don't know, it's a thin manifold. So if you have, okay, let me take another example. If you take pictures of me making faces, and you take millions of images, and you try to answer the question, what is the intrinsic dimension of the manifold of all the faces that can make, ignoring the background? The answer is the dimension of that manifold is less than 100 because it's bounded above by the number of muscles in my face, and it's about 56 or so. So it's a very low dimensional manifold, and it's true of a lot of natural data. The data is high dimensional, but it lies in a low dimensional submanifold, which may be very complicated and may have twists and curves, but it's low dimensional. So the ultimate holy grail of representation learning would be to find a parameterization of that data manifold. And the first thing you need to answer is, am I on the manifold or outside? That's what energy-based modeling tell you zero energy if you're on the manifold, higher energy if you're outside, and in fact the energy gives you some idea of the distance to the manifold. Now, if you do probabilistic modeling, if the manifold is actually thin, a thin place, your probabilistic model will have to tell you the density on the manifold is infinite, the density just epsilon outside is 0, and the integral is 1. Okay, and it's a terrible model. So in practice, what probabilistic models do is that they impose some sort of fuzziness, which you can do with simple Bayesian priors and regularization. But they basically say, I can't have like a sharp transition between like on the manifold and off. So you can think that it's a good way of doing probabilistic modeling, but in fact, the probabilistic model you're building from this is false. It gives some non-zero probability outside of the manifold, and it shouldn't. So that's why there's a bit of over-constraining conditions in probabilistic models. But again, if you're a Bayesian, you have tricks to kind of get around those problems. It just makes things more complicated.
I think we have time for one more question.
We have one in the chat. Maybe we can ask someone if we have some positive and some negative differences. One, the hybrid of contrastive and regularized work tests.
Yeah, those two things are not incompatible. You can use both. So yeah, if you have good ways to do non-contrastive and you have negative samples, yeah, you should probably do both. Absolutely.
Thank you.
All right, thank you.